All right, hey guys. What we're going to do is we're going to go through some of the things that Newton's first law is, and some of the things that you guys have looked at last week before break, looking at Newton's first law. So, what I want to start with is we're just going to kind of do a notes day today, but I also want to go back and look at the simulation that you guys looked at in terms of the forces and motion basics, and kind of look at what that was, as well as look at this. So we started with this question here. And the question says, which diagram shows a force diagram for a car traveling with a constant velocity to the right? And basically, constant velocity, what that means is something that's not speeding up, something that's not slowing down, something that's not changing direction. It's always going the same speed in the same direction. These were our four choices, basically. If we look at this, now everyone's was a little bit scrambled, but this is the general layout of what we had, right? And so here's what you guys said before the lesson. So before you guys did that simulation, here are our breakdowns. Basically, on average, we had about 17% of us actually get the question right. 16 of us, or about 70% of us, chose this answer right here, C, which is what I would expect. It's exactly what I think you think is correct. It's not correct. Most of us got this wrong. 70% of us got it wrong. Only about 17% of us actually got it correct. So what we're going to do is we're going to look at this, how the simulation showed us that this answer was correct, and then we'll kind of see how our ideas should have changed based on what we looked at. Okay, so first you guys started with this. Basically, sum of forces is another way to say net force, right? So if we add all the forces up, how does that impact the motion? And so when you see when we press go, nothing happens, right? The net force is 0. We have 50 newtons to the right, 50 newtons to the left, right? Doesn't matter what we have, as long as they are exactly the same, then the net force is 0, and so nothing's going to happen. Now, when we had this situation, we had the red team was going to win. I'm just pausing it, right? But what we see here is the speed the entire time actually is increasing as they're going. And because of that, we have a net force of 100 to the right. Now, what I asked you guys to do is I asked you to do this and tell me what's happening. Well, here we still see this moving to the right. The net force is 0. There's 100 newtons to the right, 100 newtons to the left, but it's still moving, right? And so this is what typically is harder for students to understand. It's typically harder for students to say, yes, that makes sense, right? Like, this is not hard for us to understand. Okay, they're balanced, 150 to the left, 150 to the right, like that makes sense. This is harder for us to agree with, right? Right now, the cart is moving at a constant velocity. It's not speeding up, it's not slowing down, but it's still moving in the same direction, right? The only way to get the blue team to win was to add an additional blue member, right? So the sum of my forces caused it to start moving the other way, and guess what? The entire time it's moving, it is speeding up, right? So maybe a little bit different than what we thought. And that's the tough thing with physics sometimes, is it challenges what we think is right, right? You guys are smart young men and women, but what you've maybe been taught, right, or maybe what you've thought is correct is actually not. Here's the same idea. Take the crate, we apply 50 Newton force. The entire time it is moving, but it is not moving at a constant or constantly, right? It is speeding up the entire time. Check up here, the speedometer. It's increasing. It's going up and up and up and up and up the entire time that I'm pushing it. If I stop pushing it, it just keeps going, right? Now, this simulation is trying to ignore the implication or the addition of friction. It's on a skateboard. There's wheels. There's little to no friction, right? So even though I stop pushing on the crate, it keeps moving, right? That's maybe not something that we agreed with to begin with, right? It goes back to this. Even though the net force is 0, it's still moving to the left. Here, what's the net force on the crate? It's 0. There's nothing pushing on it. There's nothing stopping it. But it keeps moving because it was already moving, right? Let's go to our answers here, right? So same question, right? We had the same question. Here's our same four diagrams, right? And now, after looking through that, we actually had about 63% of us get it right. So about 40% of us actually changed what our answer was, which is really good, right? Which is hard to do, but it's something that we need to do to have a sense of what's actually happening, right? Now, what we can look at is the second question. Describe what happens if you're riding a skateboard and hit something like a curb with the front wheels, and why. Basically, here's what I wanted you to say, right? The skateboard stops, but the person riding the skateboard doesn't stop. That person still flies forward, right? Which is weird. Nothing actually pushed this person on the skateboard forward, but it's because of Newton's first law. It's because they were already moving. Nothing stopped them, so they keep moving, right? If we look at this, the skateboard with the crate is already moving. Nothing stops it, so it keeps moving, right? So let's take a look, and let's go through some of the notes with this. I'm not sure if my image is going to stay on top. Let's see if we present it. It doesn't look like it, but that's okay. So this is what I would get down in my notebook, right? So write these down in terms of our notes. The first thing is the idea of inertia. So inertia is a word that basically means laziness in Latin. It basically means I don't want to change from what I'm doing, right? It's defined as an object's resistance to changes in motion. The more mass something has, the more inertia that it has. Basically, if something is moving, it wants to keep moving, right? This bullet hit these 4 crayons, but because it's already moving, it wants to stay moving. Something that's stopped wants to stay stopped, or something that's not moving, right? These crayons, because they are just sitting there, they want to keep sitting there. So they will sit there for just a split second after they've been shot before they actually fall, right? Now, if I go too fast, feel free to pause the video, right? Get these written down and then keep moving. Second thing, here's what we generally know. Heavy objects are hard to both start, they're also hard to stop. Right? A big boulder is hard to start moving or start pushing, right? But a big truck is also very difficult to stop moving because they have a lot of inertia. Light objects are very easy to start, but they're also very easy to stop, right? So in this case, the light car stops much faster than the truck, but the truck eventually does stop, right? If you've ever seen someone like a strong man pull a bus, right, or pull an airplane, it can happen, right? But here's the thing, once that airplane is moving, guess what? It's a lot easier to pull because once it's moving, it wants to stay moving because of its inertia. The tough thing is just to get it started, okay? That brings us to Newton's first law. You've known Newton's first law as this. An object in motion stays in motion, and an object at rest stays at rest unless acted upon by an outside force. Right? That's the general description of it. We're going to write it a little bit differently. Basically, here's what it says. When the net force on an object is 0. So, when the forces are balanced, or when there's no force at all, the object's motion will not change. Right? So what that means is it can do basically one of 2 things for us. It's really 3, but we're just going to keep it to 2. 1, it can stay at rest. It can stay not moving. An object at rest stays at rest. Or it can continue to move with a constant velocity. Right? This is known as the law of inertia because basically it wants to keep doing what it's already doing. Here's our skateboard with our skateboarder, but now it's a motorcyclist, right? The motorcycle stops. There's a force that stopped it. Why does the motorcycler keep going? Well, because nothing stopped it, and it wants to keep going, right? Its inertia keeps it going. The net force on the motorcyclist is 0. There's nothing pushing on him to stop. There's nothing throwing him forward. He just keeps moving forward because that's what he was already doing, right? I'll give you an example next time we meet of this. The tablecloth trick is a classic example of Newton's first law. You can pull a tablecloth out from underneath the table setting because the things have inertia that are sitting on the table. They want to stay at rest because they were already at rest. I think that's it. Hey, I'm back. Yeah, that's it. Okay? So make sure you get that stuff written down. What we're going to do the next day is we're actually going to ask you guys to apply it in some way, right? I don't think there's anything else that I wanted. Nope. Just make sure you get the post questions taken care of, right? And that's it. Hope you guys are having a great time, staying safe, getting outside, doing something active, right? And hopefully see you guys soon.